Hi, one more section, perhaps the hardest one for a while. Once we get past 8.3, we're going to go to chapter 11, a little bit nicer for a while. Probably 8.3 is maybe the toughest we'll do now until the end. Conditional probabilities. Now, after I taught this to the other class, I realized it probably would have been helpful to remind them probability of A given B, because later in the course somebody said, oh, why didn't you just tell us what you meant? But probability A given B is the probability of the intersection divided by probability of B, right? I mean, it was the probability that, with the Venn diagram, given that B has happened, this is the given one. So given that we're sitting in, imagine this is B, what's the probability A occurs? And the only way A can occur is in the intersection here. So it's really just a ratio of A and B occurring over B having had occurred. So this really is no different when we get to functions. We're still going to we're looking at the probability that both occur over the probability of the given. So when we do this in terms of functions, it really takes on the same idea. Think of the intersection over the marginal, or otherwise the joint divided by the marginal in terms of functions. So first I just wanted to set up an easy example so that you could kind of see what I'm doing. I'm going to flip a coin 3 times. X is the number of heads on the last flip. And you can only have 0 or 1 head on the last flip, either it's a head or it's not. And Y is the total number of heads on all 3 flips. So this is my Y, and this is my X. And here's the joint probability mass function. 0, 0 occurs 1/8 of the time. That's tail, 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 right? There's no heads totally, and there's no heads on the last toss. 3 would mean I have 3 heads, but then X equals 0 means I have no heads on the last toss, so this is impossible, and I give it probability 0. So these are just, I listed the outcomes. There's 8 outcomes, and so here's like X equals 0, Y equals 1, X equals 0, Y equals 2. So all the possibilities. The probability X is 0, I add across. The marginal is just 4/8. And the probability X is 1 is 4/8. But that makes sense, right? If you toss a coin 3 times, what's the probability last flip is a head? 4/8. What's the probability it's not a head? 4/8. In 3 flips, what's the total number of heads? You could have 0, 1, 2, or 3. 0 heads is 1/8. That's tail, tail, tail. 3 heads is head, head, head. And then these combined in the center are 3/8 and 3/8. And again, here's your marginal for Y's and your marginal for X's. And so now I want to start answering some conditional problems. I wish I could save that picture on all these questions. What's the probability the last flip is heads given 2 total heads? So here's 2 total heads. I'm sitting in here. Okay, given 2 total heads, so that's my denominator. What's the probability of 1 head on the last flip? So that's 2/8. So this is going to be 2/3. Right? If you think about it, when Y is equal to 2, there's 3 cases, and 2 of them have a head on the last flip. So in other words, what I'm trying to find is probability X equal 1 given Y equals 2, and the top is just, right, the intersection over, and so that's where we got 2/8 from, over the probability Y is equal to 2, which is 3/8. But again, we could just do it from looking at the table. I'm going to try to not go down very much farther because I don't want to lose the nice picture or the nice table we have. what's the probability that the last flip is a head given that 3 total heads are flipped? Well, it has to be 1, right? So what's the probability, let's write it out this way, that the last flip is a head given y is equal to 3. So this is the probability that x equals 1 and y equals 1 over probability y equals 3. So, oops, y equals 1, y equals 3, sorry. X equals 1, y equals 3, so x1, y equals 3 is right here, which is an 8, times the probability that y is equal to 3 is an 8. So this is certain, which kind of makes sense. I mean, if you have 3 total heads, then the last flip has to be a heads. If you have 3 coin tosses and 3 are heads, the last has to be a head. So this is a certain event. Let's go a little bit further. What's the probability that last flip is a head given that at least 2 heads have been flipped? So what's the probability that the last flip is a head given, in this case, y is bigger than or equal to at least that many? So again, that's just the intersection. Probability that x is equal to 1 and y is greater than or equal to 2, all divided by probability y is greater than or equal to 2. So y is greater than or equal to 2 half the time over probability x is 1 and y is greater than or equal to 2. So that's these two cases, which is 3/8. So 3/8. So what does this turn out to be? 3/4? Yeah, 3/4. All right, and what else do we have here? Are x and y independent? Actually, I can tell they aren't right away. I can go up here to problem B. Probability x equal 1 given y equals 3. If they were independent, then y equal 3 should have no effect on x equal 1. But it does, because given y is equal to 3, x equals 1 is 1, which is not equal to the probability that x is 1. The probability x is 1 is a half, but knowing that y equals 3 changed the probability that x equals 1. So here's just one case. I mean, anytime that we can show probability x equals x given y equals y is not equal to the probability x equals x, then we don't have independence. Remember, we said if probability A given B is not equal to probability of A, then we don't have independence because B is changing what A would happen. I mean, A is dependent on B. Whatever happens with B changes the probability of A, so I don't have independence anymore. So I don't think I have any other. Oh, I do have the determine the conditional probability mass function of x given y. So I'm trying to determine probability x, y. So this means the conditional function of x given y. And x given y. So by definition, this is the joint, which is the probability that x is x and y is y. I mean, maybe I should rewrite. I mean, this is x is x and y is equal to y. That's what the joint is, divided by y on the bottom. So that's probability, the marginal, the probability that y is y. So down here is just the probability that y equals y. So on top we have the joint. Do we have a nice function for that? Let's see. Up here, did we have a joint distribution? No, determine the conditional mass function of x given y. Well, that's what it should be, but I didn't actually have a function for x is x and y is y, do I? No. And on the bottom, the probability y is equal to y. Let's go back up here. That's just a binomial down here. Let me clean this up a little bit because I need to put something here, and then I'll be right back because this is, I think, already getting long.